Welcome to AI Paper Slop, the YouTube series for AI researchers and ML engineers, where we summarize the latest AI and tech papers. Today, we're jumping straight into the Qwen-Music technical report by the Qwen team.
Yeah, and for those of you building AI audio models or just, trying to keep up with the state of the art right now, here is the immediate TLDR.
Lay it on us.
So Qwen-Music is this new state-of-the-art framework for text-to-music and cover song generation, and it outputs actual 48 kilohertz high-fidelity stereo.
Wow, 48K. Okay.
Right. And the real architectural breakthrough here is how they split the generation pipeline into three entirely distinct parts.
So not just one massive end-to-end blob.
Exactly. First, you have a 0.6 billion parameter tokenizer that aggressively compresses the audio down to a 25 hertz stream.
Which is tiny.
It is. Then second, they use a 3 billion parameter LLM that relies on a novel melody chain of thought. And this explicitly plans out vocal contours before it even tries to generate the full song.
Oh, that is fascinating. And the third part?
The third part is a 1.3 billion parameter diffusion transformer renderer, and that's paired with a frequency-aware spec VAE.
And I'm assuming the results back up this architecture.
Oh, absolutely. I mean, in blind A/B testing, it essentially achieves parity or even beats leading proprietary models like Suno V5.5 and Minimax.
That is huge.
Yeah.
I mean, if you work in generative audio, you are already intimately familiar with the semantic-acoustic gap.
Oh, yeah. The bane of our existence.
Right. It is the core bottleneck in the field right now. Because on one hand, you have the semantic side of music.
The lyrics, the chord progression, the overarching song structure.
Exactly. But then on the other hand, you have the acoustic rendering, like the actual physical timbre of the singer's voice.
Or the phase alignment of the bass line.
Yeah, or the high-frequency cell of a crash cymbal. And forcing a single neural network to predict the overarching poetry of a song while, simultaneously calculating the phase of a waveform at 48,000 samples per second.
It's just a nightmare for model capacity. It really is.
Right, so you need a highly efficient tokenizer to fix this.
Exactly. The entire system hinges on finding a highly efficient, discrete language for the LLM to use.
So how does the Qwen-Music tokenizer pull this off?
Well, it takes the raw 24 kilohertz waveform and compresses it down into this 25 hertz single codebook stream of music semantic tokens.
Let's actually pause on that 25 hertz number for a second. Because for the ML engineers listening who deal with context windows all day, I mean, that is the magic number.
It's incredibly efficient.
Yeah, at 25 hertz, a 3-minute song is only, 4,500 tokens?
Yep. Around 4,500.
You can easily fit that into a standard LLM context window.
Yeah.
You don't need any insane, sparse attention mechanisms. But usually, getting audio down to that level of compression just absolutely destroys the high-frequency detail.
It does. But the Qwen team mitigates that data loss by using a 24-layer, 0.6 billion parameter conformer backbone.
Okay, a conformer.
Yeah, and they train it in 4 highly specific, really methodical stages.
So walk us through stage 1.
So stage 1 is bidirectional self-supervised pre-training using BestRQ, which that's just mask prediction with a frozen random projection quantizer.
Wait. I'm stuck on stage 1 already.
What's the holdup?
Well, if the end goal of an LLM is autoregressive left-to-right generation, why on earth are they wasting compute training the encoder bidirectionally?
Ah, I see what you mean.
Doesn't that just teach the model to rely on future context that it literally won't have during inference?
I mean, it definitely seems counterintuitive at first glance, but you have to remember the loss landscape of global music representation is incredibly complex.
Okay, fair.
Training a causal model from scratch takes significantly longer to converge on good global features because it's constantly guessing blindly into the future.
So it's flailing around trying to learn the structure.
Exactly. By using a bidirectional pass first, the model learns this deeply robust understanding of how a chorus relates to a verse, or how a buildup resolves into a drop.
Oh, I see.
Then, in stage 2, which they call causal adaptation, they simply take that converged checkpoint and switch the self-attention from bidirectional to causal.
So they just mask out the future context in the attention layers.
Yes, exactly. Left context only. It prepares the model for autoregressive generation at a fraction of the compute cost.
While keeping all that rich acoustic feature extraction it learned when it was, allowed to cheat and look at the whole song.
Right. It's a fantastic trick for saving GPU hours.
Okay, so that's stage 2. What happens in stage 3?
Stage 3 is multitask supervised fine-tuning, or SFT. They attach 3 different heads to the 25 hertz encoder outputs.
What are the heads?
There's a CTC head for lyrics, a Mel spectrogram head, and a chroma head for 12-bin musical harmony.
And this is where the representations are basically forced to bridge that semantic-acoustic gap we mentioned earlier.
Precisely. By forcing the network to minimize loss across all 3 targets simultaneously, the latent space literally has to organize itself around both human language and musical theory.
And using CTC loss connection as temporal classification for the lyrics is so crucial here.
Oh, yeah. Completely necessary.
Because, I mean, audio and lyrics aren't perfectly aligned frame by frame. A singer might hold a single vowel for 5 seconds, right?
Or cram 10 syllables into 1 second, like a rap verse.
Exactly. CTC loss dynamically handles that unaligned mapping, so you don't need manually time-stamped lyric data sets, which is huge for scaling up training.
Totally.
Yeah.
And then we arrive at stage 4, which is injecting the actual bottleneck. They insert a single vector quantized, or VQ, codebook with 32,768 entries.
But wait, if you just slam a hard VQ bottleneck into a fully converged continuous network, the gradients usually explode, right?
Oh, yeah, it's a mess.
You've induced catastrophic forgetting and just destabilized the whole encoder.
Yeah, so the engineering solution here is a smooth ramp-up. They blend the quantized discrete path with the continuous path using a scalar gate.
Oh.
During training, this gate ramps linearly from 0 to 1. So as the gate gradually closes off the continuous information, the downstream layers are slowly forced to rely entirely on the discrete tokens.
Preventing the sudden instability. It's brilliant. I mean, to use an analogy, it's kind of like teaching a student to read sheet music, right?
Wow, so.
Well, first you let them look at the whole piece of sheet music to understand the theory, right? That's the bidirectional best RQ in stage 1.
Right, getting the global context.
Then you force them to read it left to right in real time. That's the causal adaptation. And finally, you test them on singing the lyrics and playing the chords simultaneously during the multitask SFT.
That is actually a really perfect way to frame it.
So, okay, we have successfully compressed complex audio into a stable 25 hertz token stream. The music is now tokenized into a language the LLM can natively speak.
Right, and this is the foundation for the 3 billion parameter LLM, which is based on Qwen 3.5 Omni.
And this brings us to what I think is the paper's most significant contribution, the melody chain of thought, or Melody-CoT.
Yeah, this is the really exciting part. Because the core challenge of text-to-music generation is the ambiguity of text prompts.
Right. Text is just so low bandwidth compared to audio.
Exactly. If you prompt a model with, a beat pop song with a catchy female vocal, you have given it a vibe, sure.
But you haven't given it a melody.
Exactly. Previous models essentially had to guess the arrangement and the melody simultaneously at the token level.
Which is why AI music often just meanders endlessly. The song wanders aimlessly because the model is literally making up the tune word by word.
Yep. Qwen's Melody-CoT changes this by explicitly training the LLM to generate an intermediate sequence of melody tokens before it predicts the full mixture semantic tokens.
Oh, man. It's the equivalent of a songwriter sketching out just the lead vocal hum on a napkin, right? Just doing that before handing it over to the orchestra or producer to fill in the rest.
That's exactly what it is.
But practically speaking, how do you even create a data set of pure melody tokens from raw audio mixes?
The data pipeline for this is fascinating. They use an external pitch extraction model called RMVPE to pull a 50 hertz pitch curve from the training audio.
But 50 hertz resolution is way too granular for structural planning, isn't it?
Way too granular. It captures every tiny vocal waver, every breath.
Every bit of vibrato, which you don't want the LLM focusing on. You want the LLM writing the underlying sheet music, not micromanaging the singer's vocal cords.
Exactly. So they downsampled that 50 hertz pitch curve by a factor of 8, taking it down to a 6.25 hertz sequence.
Okay, down to 6.25. And they use median pooling for this, right? Let's highlight why they use median pooling instead of average pooling.
Yeah, that's a key detail.
Because if a singer's voice cracks for like a fraction of a second, an average pool will pull the whole pitch value off center.
But a median pool completely ignores that outlier frame. It leaves just the core structural note.
Right, so the downsampling leaves a super clean melodic contour.
But they don't use absolute pitch for this contour. They convert it into a relative MIDI representation.
Explain how that works.
They compute the median MIDI value over all the voice frames in the sequence, and then they just subtract that median from every single frame.
Okay.
So the result is a sequence of relative semitone offsets rather than absolute notes.
Now, I actually have to push back on this approach a little bit.
Yeah.
Because the industry standard for melody conditioning, like in models like ControlNet for audio or other papers, is using standard chromograms.
True. Chromograms are very common.
Right, and they are well understood, so why go through the extra mathematical headache of creating relative semitone offsets?
Well, the problem with chromograms is conditioning leakage.
Leakage?
Yeah. A chromogram is extracted from the acoustic waveform, meaning it often retains residual background noise or chordal harmony or even the specific timbre of the original singer.
Oh, I see.
If your conditioning signal contains absolute pitch, key, or that acoustic residue, it acts as an overly rigid guide. The model starts completely ignoring the user's text prompt.
So if I prompt for a gritty male rock vocal, but the chromogram leaked the high-pitched female pop vocal from the training data, the model gets confused and tries to split the difference.
Exactly. But by reducing the condition to a relative semitone offset, the melody tokens discard all absolute register and timbre information.
So the model is forced to obey the user's text tags for style and arrangement while simply following the mapped-out structural tune.
Right. And to train the LLM to generate these blueprints, they use two distinct patterns.
Okay, what's the first one?
The first is the section level pattern. The model is trained to write melody tokens only for vocal sections that contain lyrics, like a verse or a chorus.
And for instrumental sections.
It outputs a special placeholder token.
Makes sense. And the second pattern?
The second pattern is where the real generalization occurs. They call it the unique section level pattern.
Unique section level?
Yeah. Instead of the LLM predicting the melody for every single chorus as they happen chronologically, it samples just one representative melody segment for a recurring section label.
Oh,
yeah.
This prevents the model from turning into a mindless copy machine.
Exactly.
If you force the LLM to just output, here is the blueprint for the chorus, and then later in the song it just says, refer back to the chorus blueprint.
Yeah.
The model has to learn how to dynamically reuse that melody.
Instead of just memorizing a 3-minute sequence frame by frame.
It teaches the LLM the concept of a musical motif.
Yes, it forces structural coherence. The model understands that the second chorus should melodically mirror the first chorus, even if the underlying chords or the drum energy changes.
That is genuinely brilliant. Okay, so our 3 billion parameter LLM has successfully written the semantic tokens and planned out a beautiful melody.
Right.
But semantic tokens are heavily compressed. If you listen to a 25 hertz discrete token stream, it sounds like absolute robotic garbage.
Oh, it's totally unlistenable.
We still have to inflate this blueprint into a lush 48 kilohertz stereo waveform. How do we actually render the audio?
So the renderer, Qwen-Music render, is a 1.3 billion parameter diffusion transformer, or DIT.
Okay, DIT.
It takes the discrete music semantic tokens from the LLM alongside the user's text prompts, which are encoded via a Qwen-3 embedding model, and it predicts continuous acoustic latence.
And to control adherence to the text, I assume they employ classifier-free guidance, or CFG.
They do, but they use a highly specific strategy called text drop CFG.
Text drop CFG. How does that differ from normal CFG?
During the unconditional forward pass of the diffusion process, they drop the text condition, but they retain the language model tokens as the primary scaffold.
Oh, you have to keep the LM tokens during the unconditional pass.
Yeah.
Because if you drop the semantic tokens alongside the text, the diffusion model would have no structural grounding at all.
Exactly. The song would literally collapse into unstructured noise the moment you adjusted the text guidance scale.
That makes total sense. So once the DIT predicts those continuous latents, they go into a spec VAE decoder to reconstruct the high-resolution spectrograms.
Yeah.
And here is where we get into some heavy but really brilliant signal processing physics. Because standard neural network activation functions usually treat all data equally.
Right, but an audio spectrogram is fundamentally a map of physical frequencies.
Exactly. So how do they handle that?
The Qwen team upgrades the big VJAN architecture by using what they call the spec snake beta activation function inside the decoder.
Spec snake beta.
Yeah. It parameterizes its variables along the frequency axis. Crucially, it uses a log frequency prior that encourages stronger periodic modulation at higher frequencies.
Okay, unpack that log frequency prior for us. Why do higher frequencies actually need more periodic modulation from the activation function?
So in a spectrogram, a short-time Fourier transform, or STFT bin, corresponds to a fixed physical frequency. High-frequency audio, like a cymbal crash or vocal air, literally oscillates faster in the physical world.
Right.
Standard activation functions struggle to reconstruct that rapid oscillation, which is why AI audio often sounds muffled or metallic in the top end.
So by giving the activation function a log frequency prior, it physically adapts.
Yes. It applies a stronger periodic bias to the upper STFT bins, allowing the network to effortlessly reconstruct that high-end sizzle.
And they don't even stop there. Right before the final inverse STFT synthesis, which is the step that actually turns the spectrogram back into an audio waveform, they pass the output through a band mode refiner.
Right.
This is a convex 1D module that corrects the decoder's output by specific frequency bands.
Sounds so clever.
It applies phase-only correction for the low-frequency band, joint magnitude and phase correction for the mid-band, and magnitude-only correction for the high-frequency band.
It is a pure reflection of human psychoacoustics.
Seriously. If you've ever tried to mix an EDM track, I mean, you know exactly why this matters.
Oh, 100%.
Low-frequency sub-bass is entirely about phase alignment. If your bass waveform is out of phase, the speakers push when they should pull, and the track completely loses its physical punch.
Yeah.
So the model dedicates its low-end correction entirely to fixing phase.
Conversely, human ears are physically incapable of detecting phase differences at, say, 15 kilohertz.
Right.
For a hi-hat or a cymbal, we only perceive the magnitude, the raw amplitude of the energy.
So forcing a neural network to calculate and correct phase at 15 kilohertz is just a massive waste of model capacity.
Exactly. The band mode refiner saves compute and improves quality by only correcting what human ears actually care about in each specific frequency band.
It's incredibly logical from a signal processing standpoint.
Yeah.
But all this intricate architecture, the Melody-CoT, the band mode refiner, the 25 hertz compression, it means absolutely nothing if you train the model on bad data.
Garbage in, garbage out.
Exactly. And since we are on AI paper slop, let's talk about how the Qwen team filtered their 5 million hour training data set to avoid feeding the model literal slop.
Well, the quiet killer in high-fidelity audio generation is fake high-res data.
Oh, yeah.
The internet is littered with 128 kilobit MP3s that were upsampled to 48 kilohertz by some random user and saved as lossless FLAC files.
Or mono tracks simply duplicated into the left and right channels and passed off as stereo.
Right. And if you train a high-fidelity renderer on upsampled MP3s, the model learns to generate those muffled, compressed-sounding MP3 artifacts as if they're a natural part of music.
And container metadata is useless here. The file's metadata will swear up and down it is a 48 kilohertz track.
They could lie to you.
So how do you detect an upsampled MP3 algorithmically across 5 million hours of audio?
They built this noise floor-aware cutoff detector. So an old, highly compressed MP3 has a hard frequency wall. It simply deletes all audio data above roughly 16 kilohertz to save file space.
Okay, so they look for that wall.
But they do it smartly. The Qwen team takes a track and samples the very edges, the first and last 10% of the audio, to estimate the true baseline analog noise floor of the original recording.
Because even in a silent room, microphones have a tiny bit of analog hiss.
Exactly. Then they scan the internal, non-silent portions of the track, looking for a sudden, severe decibel drop-off relative to that specific noise floor right around the 16 kilohertz mark.
Oh, wow.
By comparing the internal audio's frequency response to the edge noise floor, they can mathematically prove that the high frequencies are missing due to compression, regardless of what the file format claims.
It is literally like a forensic detective finding the original compression artifacts hidden under a fresh coat of upsampled paint.
That's exactly what it is. And once they have this pristine, verified data, they apply a highly structured LLM training curriculum.
How does the curriculum work?
They use an internal reward model to score the data and bucket it into 7 quality tiers, Q1 to Q7. They start pre-training broad, using buckets Q3 through Q6 to teach the model general musical concepts.
Getting the basics down.
Yep. Then they anneal on Q2 and finally refine the model purely on the pristine Q1 data.
And the post-training pipeline is equally rigorous. Right?
Very. They establish a clean instruction following baseline using supervised fine-tuning. Then they move to offline direct preference optimization, or DPO.
Right.
And then they finish with online GSPO.
Group sequence policy optimization. Now, why the shift from offline to online optimization at the very end?
Well, offline DPO is great for teaching a model basic preferences based on static data, but music generation is highly complex and multimodal.
Sure.
Online GSPO allows the model to actively generate multiple different trajectories for a single prompt during training, and then mathematically evaluates the distribution of those generations.
So it's pushing the boundaries on fine-grained musicality because the model is exploring its own generation space.
Exactly. Learning what makes a track sound truly professional rather than just mimicking a static data set.
Which brings us to the ultimate question. All this theoretical architecture and data filtering has to translate to actual human ears. How does Qwen-Music stack up against the proprietary heavyweights?
They conducted blind A/B testing with 50 professional human raters, and
Yep.
specifically music producers and creators, not just random listeners.
And the results?
Qwen-Music beat Minimax Music 2.6 with a 66.7% win rate. It beat Marika V8, and it beat Suno V5.
Wow. What about Suno V5.5?
Against the current reigning champion, Suno V5.5, it achieved a 50.3% win rate. It functionally ties or slightly edges out the best proprietary model in the world in professional preference.
And we know this holds up outside of their internal testing because they quietly put this model on the artificial analysis music with vocals leaderboard under the alias JazzCat.
Yep, the classic alias move.
Right, and it hit number 3 for English vocal music against all the leading closed source systems.
But the evaluation gets even more interesting when we look at cover song generation. Because of the Melody-CoT we discussed earlier, the model is uniquely equipped to take a melody and completely rearrange the genre.
They evaluate this capability using a metric called Melody, MAE, right?
Yes.
Now, I always wonder how researchers objectively score a cover song. I mean, subjectivity plays such a huge role in music appreciation. How do you mathematically prove a cover song is good?
You measure how well the AI preserved the original tune using dynamic time warping.
Dynamic time warping.
Yeah. When an AI generates a cover song, say turning a fast pop track into a slow acoustic ballad, the tempo and rhythm change completely. You can't just overlay the two audio files to compare them.
Right, that wouldn't match up at all.
So dynamic time warping algorithmically stretches and squishes the time axis of the generated cover song's relative MIDI until the peaks and valleys align with the original song's MIDI.
It's like finding the core skeleton of the melody, regardless of how much the AI stretched the phrasing. It's basically a mathematical karaoke score for the AI.
That's exactly it. And once the sequences are aligned in time, they calculate the mean absolute error, the MAE. It calculates exactly how many semitones the AI drifted from the original singer's pitch.
And what do they find?
They found that the section-level melody conditioning clones the original melody the most accurately, yielding the lowest MAE.
Okay.
However, the unique section-level conditioning, which only gives the AI one chorus blueprint to work with, actually allows the model to better adapt to extreme genre tags.
That makes perfect sense. If you give the model too rigid of a guide, it struggles to morph a rigid pop song into a swung jazz rhythm.
Right.
But if you just give it the motif, it can swing the rhythm, adapt the underlying chords, and truly reinterpret the song.
Exactly.
Before we wrap up, I want to quickly highlight the intelligibility score. It achieved a phone error rate, or PER, of 6.0, which is second only to Suno V5.5.
That's incredibly impressive.
It is. Getting a diffusion model to output clearly understandable lyrics without slurring the vowels is notoriously difficult, so that is a massive win for the Tokenizer and the CTC loss implementation.
Absolutely. Looking at the entire system, the Qwen team has proven that decoupling semantic planning from acoustic rendering is the path forward for AI audio.
Yeah, the Melody-CoT forces the LLM to think structurally like a composer, and the frequency-aware Spec VAE renderer ensures the final output is acoustically flawless.
It really is a masterclass in pipeline architecture.
It really is. And I want to leave you with a final provocative thought based on what we've discussed today. Right now, Qwen-Music uses median pooling to intentionally strip away vibrato and micro-expression.
Right, leaving just the core MIDI melody.
Exactly, for structural planning. But what happens in a year or two when future researchers apply a second layer, let's call it expression COT?
Oh, man.
Imagine a model that first plans the melody and then uses a second chain of thought pass to explicitly map out the breathiness, the subtle vocal fry, and the emotional timbre before rendering.
That would be wild.
If we can mathematically plan the emotion of a vocal take just like we plan the melody, how much closer does that get us to true AI session musicians? Something to mull over as you read the paper. Thank you for tuning into AI Paper Slop, and be sure to check out the full Qwen-Music technical report.